now in chapter 12, chapter 12 is basically Newton's first law on steroids, because now we're not just talking about translational equilibrium, we're talking about rotational equilibrium. Okay, and so the first idea, the beginning of the packet, the first couple of slides are reiterating this idea of torque, how we find torque. We take the lever arm and we use the right-hand rule, put our fingers in the direction of the lever arm, curl in the direction of the force, and that gives us the torque. And so equilibrium conditions, here's what this means now. If we have translational equilibrium, that means the net forces horizontally and the net forces vertically equals 0. So you can write sigma F equals 0 for X and for Y, and there we have translational equilibrium. And then this is what's new. If we have rotational equilibrium as well, then that means the net torque is 0. So we write sigma tau equals 0. And then those are our equations for dealing with equilibrium problems. The net force is 0, the net torque is 0. We just fill them in with all of the forces, all the torques, and then we're able to solve for the missing forces. That's what this chapter is going to look like. We want to keep in mind that when we're solving the problems with torque, we can pick the axis of rotation. And what we're going to do is we're going to try to pick an axis where there is an unknown. For example, if there's an unknown quantity, some unknown force, we're going to choose the axis of rotation to be right there. That thing will disappear, and then we can find some other unknown quantities using the torque equation. So when you're solving a problem, you need to specify what axis you're using. And let's get into some of the examples. So here's example 1. And we want to find where this person should be sitting in order for it to be in equilibrium. And so what's the best place to choose as our axis of rotation? That's going to be center, right here. That's going to be nice for a couple of reasons. One, the normal force then will have 0 as the radius, and the force of gravity on the plank will be 0. So ultimately, the net torque is 0. So that means that mg, and this is pulling this way, right? This is positive rotation, so that's positive. Plus the mass of the plank times g plus the normal force. This should be times 2. mg2, because this is 2 meters. This is 0. This is 0 torque. And then minus big M times g, and then x. This is the torque. This is the weight of the person. And then this is the distance from the center. And this is negative, because this is turning it clockwise. That's a negative rotation. And so when you end up solving for it, so you get mg2 equals mgx. So x equals little m times 2 over big M. And that's it. That's the solution to the first question. Now for example 2. We have this situation. We have the window washer on a plank. It's hanging from 2 ropes. We have the left rope and the right rope. So I have FL and FR. And then we have the weight of the platform itself. And here is the weight of the window washer, standing 1.5 meters from the left. And so I want to know these 2 things, so I have 2 unknowns. Well, I can write sum of the torques is 0, and I know the sum of the vertical forces is 0. So all these forces are going to add up and equal these forces, and all the positive torques will cancel out with all the negative torques. And I can choose any axis that I want. I'm going to choose this as my axis because I know these distances from here, and then that'll cancel out this one. If I cancel out this force, and I can solve for this one, then I can use this equation to plug back. So here's what we're going to do. We write this out for the torques. If this is the 0 point, then there's no torque from that force. This is pulling this way. This is a negative torque. So this is negative 700 newtons times 1.5 meters. And then again, this is a negative torque. It's pulling clockwise, so that's negative torque, 800 newtons times 2 meters. And then I'm going to add this torque over here. This is Fr times 4 meters. Now I just solve for Fr. When you do that algebra, you end up with, this is physics, right? Set it up, that's the physics part. The rest of it is just algebra and arithmetic. You get 662.4 newtons. Okay. So I use the torque equation to help me find Fr. Now I need to find Fl, the leftward force. And so the vertical forces all add up to 0. What are all these vertical forces? I have Fl, and Fr is the other vertical force upwards, 662.4 minus 700 newtons, right, vertically, this is going down, 800 newtons. All of these put together give you 0, and that vertical force is 0. So that ends up being 837.5. I think this should be 5 also. So now this is example 3, with the person holding the ball. So here there are only 3 forces. There's the elbow joint, there's the bicep muscle that attaches in here, and here's where the weight is. You can tell it's actually kind of a disadvantage to have the bicep muscle where it is. The farther out the bicep muscle is, the more torque you'd have. And actually other animals, their bicep muscle is attached further out here, and as a result, they're stronger. Their muscles aren't actually stronger, but they can lift more weight because they can create more torque because of where their bicep muscles are attached to their bones. Okay, and so how do we solve this problem? We want to find what F and R are. Right? I want R to cancel out, so as a result, I'm going to make this my 0 point for calculating the torque. So the net torque is 0. So what are my torques? Well, R times 0. This one is pulling up this way. This F is pulling up. So that's R cross F. This is positive. Plus F times 0.03. That's the R, that's the distance. And then this one, the 50 newtons is pulling in the negative rotational direction. So minus 50 newtons times 0.35. So, yeah, that's right, though. Student can interaction help solve them. Now back to the video. And so when we do this, second lab class is just starting. And so here, this is 0. Now I can solve for F, right? 0 equals this. So it turns out that force, the force of the bicep, is 583 newtons. So you can see the inefficiency here. We have to exert, the muscle itself has to exert 583 newtons of force to lift a 50 newton object. Okay, so now we're looking for R. Here we can set up that the net vertical force is 0. What are the vertical forces? We have R pulling down, we have F pulling up, which is this, and we have this force pulling down. The 2 down forces, the up force, a little bit of quick algebra, and we get that R equals 533. That's example 3. Okay, so in this problem now, we've got to be really careful with our diagram and with the labels that we use and paying attention to direction and angles and that kind of thing. So here I'm just going to start by writing all the sigma F equations in sigma tau. So sigma Fx, so the horizontal forces here, what are they? There's only the friction, and we'll make right positive, so F is positive. The other force is the force of the wall, which they've labeled P, pushing that way, so minus P. That's it. The normal force and the force due to gravity are the only other forces, and those are vertical. So we put those into sigma Fy, and we have the normal force minus Fg. The wall is said to be frictionless. If there was friction, then there might be some vertical forces from the friction on the wall, but there's not, so we're not analyzing that. It simplifies the problem quite a bit to have that. Now, the net torque. This is where things get kind of interesting. These all equal 0. Since we're in equilibrium, we can put the zeros in. The net torque is 0, so what are the forces that are causing torque on this? Well, if we set this as our axis, then we can ignore these two forces. So the axis is down here, so we're looking at how this is. That means these two forces, these two torques, have to balance out. This one, the force is Fg. Now I'm going to go over here and make a little diagram because I want to know what's the lever arm distance. If this is Fg, I want the component of the lever arm that's perpendicular to the force. That would be this component. And if this is theta, this component here is the length, which is 5. This is 5 from here to here. This is 5 cosine of theta. Because we need to be careful, right? We're not looking here at the angle of the action between the force and the lever arm. What we're looking at is the angle this is making with the ground. This is the perpendicular component of this that's perpendicular to the force. So this is the R that I'm going to use. So this is Fg times 5 cosine of theta. And this is positive because it's pulling this way, right? So that's a positive torque. This one is a negative torque, so make it negative, and it's P. And now that distance, again, the perpendicular component to the force. So the force is going this way. The component that's perpendicular would be this. If this whole thing has a length of 10, this is 10 sine of theta. So here's theta, that's 10 sine theta. So that's P times 10 sine of theta. I now have 3 equations. And the first thing I can find now is, I know that this is 50, because it's a 50 Newton ladder. So if this is 50 Newtons, then I can find P. So I can take this equation, and I get 50 times 5 sine of 50 degrees equals P, this is cosine, P sine of 50 degrees. When you solve for P, you get 21 Newtons. Once I know this, now I can find what the friction force is. So now I come over here, and P is equal to that friction force, so that's 21 Newtons. And I also know what the normal force is because I know that this is 50 Newtons. So, and this one I could have done right away, but I saved it for last. So Fg equals N, which is 50 Newtons. Now we've found P, the force of the wall, the force of friction, and the normal force from the ground on the ladder. Okay, so the last example here. This is what the free body diagram, it's not the technical free body diagram because I have broken these up into components, right? I took the tension, I found the vertical and horizontal. I need to split everything up. And here, this is one force, and it's at an angle, but I don't know what it is. So I'm looking at this, everything vertical and horizontal, and this is my key now for setting up my equilibrium equations. And so I'll just start. Sigma Fx is 0, and what are all the horizontal forces? There are two. There's the horizontal force from the tension. We'll make that negative t cosine 53 plus the force from the wall. Now, the wall is exerting a horizontal force. How do we know? Because there's a horizontal force from the tension. So that has to be balanced out by the wall. So plus, we're just going to call that Fx for now. Okay. Sigma Fy equals 0. What are all the vertical forces? I've got Fy, t sine of 53, those are the two vertical forces, and the two positive vertical forces. And then these are the two negative vertical forces. Minus F man minus F beam. I know this is 600, and I know that that's 300. That'll be useful later. But I still have, now I have three unknowns into the equation, so I can't do anything yet. But now I set up the torque equation. Net torque is 0. I will take this point as my axis of rotation. If I take this point as the axis of rotation, then let's look at this one first. R cross F into the board. So this is negative. So F man and his distance is 1.5 meters from the edge. Negative. And then minus the beam also will have negative torque here. And so the beam is 2.5 meters from the edge. So F beam times 2.5. Again, that's 300. This is 600 plus the torque from here. So this is T sine 53, the vertical component of the tension, times the radius, the distance from the axis of rotation, which is 5 meters. Now in this equation, the only thing I don't know is t. So I can rewrite this way. I'll put this up here. T sine of 53 times 5 equals 600 times 1.5 plus 300 times 2.5. And when you solve for t, you end up with 382. And so now I know t, so I can plug t into here and find fx. I can plug t into here and find fy. So when I do that, okay, this is 382 cosine 53 equals 230 newtons. So that's fx. And then this one, solving for fy, I get that fy is negative 382 sine of 53 plus 600 plus 300. And for that we get about 595. So that's fy. Now I want to find what f is. So the magnitude of f will be the square root of 595 squared plus 230 squared, and we get 638. Theta is going to be the inverse tangent of the vertical over horizontal. So that'll be 595 over 30. So we get an angle of 68.8 degrees. And that is the force from the hinge, magnitude and direction. Okay, so you can see there's a lot to this unit. It's really just one rule, just applying what we've learned before, but the various situations that we're going to see can be quite different. Things to keep in mind. A force causes acceleration. An unbalanced force causes acceleration. An unbalanced torque causes angular acceleration. Okay, and the unit for torque is Newton meters. And we can see why, thinking about torque, we can see why it's best when you're opening a door to push from the side of the door that's farthest from the hinge. And that's where doorknobs are, right? Doorknobs are on the edge of the door. They're not in the middle of the door, unless like you're a Hobbit or something like that. Some of their doors, the doorknob's in the middle. And that was a fashion at one time, putting doorknobs in the middle, but it didn't make any sense practically. So doorknobs are as far from the hinge as possible so you can get the most torque. What are you doing? You're increasing the lever arm distance and increasing torque. Don't forget that torque is a vector quantity, the positive, the negative, clockwise, counterclockwise, and we find that positive and negative by using the right-hand rule to determine the direction of torque.